Okay, so welcome back to another video. So in today's video we have the following equation: 2 to the power sine theta plus 4 to the power sine theta equals 8 to the power sine theta, and we want to solve for our values theta such that it's inclusive between 0 and 2 pi. And the way I also did a similar problem like this long time ago where it was 4 to the power n plus 6 to the power n equals 9 to the power n. Now, of course, those two are not the same in terms of trying to solve for your variables, but you know, the layout's very similar. And the way to approach this is that I'm going to rewrite our bases in terms of 2's. And we're going to convert this such that we define this as a variable equaling that base. And of course, we're actually, there's going to be a special constant that's going to be used. And then there's also a bunch of other techniques that the natural log is actually going to be involved, and some other trigonometric properties as well. So with that, let's start off by rewriting our basis of 2. So 2 can just stay the same way it is when we know that 4 is, equal to 2 squared, and we know that 8 is equal to 2 to the power 3. So now if I substitute everything back in, so I'll have 2 to the sine theta, then plus, so 2 squared, then sine theta, and then plus 2 to the power 3 sine theta. And if we use our rules of our power rules of exponents, so we can write this as 2 to the sine theta, then plus, well, that's supposed to be equals over here. Then it would be 2 to the power 2 times sine theta, and then equals 2 to the power 3 sine theta. How about I'll define the variable. I'll call this lowercase gamma. I'll let that equals 2 to the sine theta, okay? And then from here, that means everything will be in terms of gamma, so therefore I will have gamma plus gamma squared, and then that's equal to gamma cubed. And what I can do from here is that I'll just divide everything by lowercase gamma, and then we'll have just 1 plus gamma, and then equals gamma squared. And this is actually very interesting. So what I can do from here is I can actually solve for our values of gamma. So that means I'll write this in a form of a quadratic polynomial. So we have, if I were to set everything equal to 0, so I'll have gamma squared minus gamma, and then minus 1 equals 0. And of course, this is a very similar polynomial, because if you were to solve for the values of gamma, and using quadratic formula, you'll get that gamma is actually equal to 1 plus n minus the square root of 5, and then divided by 2. So we have two different values of gamma. So I'll replace gamma back with 2 to the power sine theta. So that means we have 2 to the sine theta. That's equal to, we'll set one of the values 1 plus the square root of 5 divided by 2. And then the other 2 sine theta, that's also equal to 1 minus the square root of 5 divided by 2. The goal here is that we want to find our values of theta, correct? And now, of course, to see this, we can actually take the natural log of both sides, but we're going to exclude the 1 minus square root of 5 divided by 2, simply because this is going to be a negative number, and you can't take the natural log as a negative number, as those things are not defined / non-existent. All right, so now we're just gonna focus on this part here. I'll just have that underlined. So that means I'll take the natural log of 2 to the sine theta, then that's equal to the natural log of 1 plus the square root of 5, then divided by 2. Of course, then I'll just use our rules of natural log, so the exponents go out to the front. So we have sine theta of ln of 2, and then that's equal to. So I'll just rewrite this using our rules of natural logs. This is under division, so it's a difference of natural logs. So this will be the natural log of 1 plus the square root of 5, then subtract with ln of 2. And then I can just divide by natural log of 2 to both sides. And then you'll see that we just have sine theta equals, let's see, so it'd be the natural log of 1 plus the square root of 5, then divided by the natural log of 2, and then this will just be subtract from 1. So now let's just take the inverse sine to both sides, and we'll get that theta is just equal to arc sine. I'll write it as that. Arc sine, so I see it, yeah. Arc sine of 1 plus the square root of 5 divided by 2, or divided by, oopsies. Let's see, the natural log of 1 plus the square root of 5, then divided by the natural log of 2, then minus 1. Okay, so that's basically one answer. However, because we're dealing with our domain from 0 to 2 pi, if you were to sketch this through our unit circle, you'll see that there's actually 2 values of theta. And if I actually rewrite this, if we were to draw this out, for example, so we have here, let me make this a little bigger. So really, basically we have 2 values of theta. Theta will have to approach over here, and then theta would have to approach over here as well. So this will be pi, that's 0, and then that's pi over 2. Okay, so we have 2 values of theta, so we actually have to consider this part of the value as well. Really what I can do is basically just subtract pi and then subtract our input. So really I'll call this, let's call this capital phi as the second value. So this will be equal to arc sine, and I'll subtract pi. So that would have to mean, so we have pi and then minus this, our input. So ln of 1 plus square root of 5, then divided by ln of 2, subtract 1. And the neat thing is that this is actually a special calculation when you evaluate this out. I'm not gonna do the work, and even so, I try to perform this and it gets really messy, so I have to look this up. This value actually approaches, well, I wouldn't say approaches, it's approximate to the natural log of 2. So therefore, that means I can just replace everything with the natural log of 2, and we have our 2 answers. So we have that theta is just equal to the arc sine of the natural log of 2, and then our capital phi is equal to the arc sine of pi minus the natural log of 2. And there we have it. That's our final answer for our thetas that satisfy the following equation over here. Yeah. So that's pretty cool if you ask me.